From a design drafted in secrecy more than 10 years ago, an unmanned aerial vehicle shaped like a stealthy flying wing has now started to appear in open-source imagery at bases located at 12,100 feet in Tibet. No sound, no pilot on board, only the cold curves of aerodynamics and artificial intelligence remain. This is the Hongdu GJ-11, nicknamed Sharp Sword, a symbol of how China is redefining the modern security landscape through data, algorithms, and uncompromising precision. In this feature, we will explore how a program that once operated in silence has become an emblem of intelligent warfare, from foundational technologies and design to the vast deployment networks that support it, revealing a broader picture of how technology is reshaping global dynamics. Join Top 10 Discoveries Official as we examine the Hongdu GJ-11 right after this. Disclaimer: the content is based on open-source materials and publicly available documents for the purpose of technological and strategic analysis. Any performance figures mentioned, such as range, payload capacity, or naval integration, are estimates derived from open sources and are not official specifications. This video does not promote conflict and does not provide instructions on how to build or operate weapons. Around the year 2009, while the world watched the rise of stealth UAV programs in America and Europe, a quiet project was taking shape in China, codenamed Sharp Sword. The program was jointly developed by Shenyang Aircraft Corporation and Hongdu Aviation Industry Group, both under the state-owned aerospace giant AVIC. For years, the entire research process remained classified, surfacing only through conceptual renderings and fragments of open-source reports. The origins of Sharp Sword stem from a clear strategic goal: to create a stealthy, highly automated platform that reduced dependence on human pilots, aligning with the global shift toward UCAV's unmanned combat aerial vehicles capable of autonomous strike operations. Such a system required not just advanced aeronautics, but also seamless integration of AI, sensor data, and automated control algorithms. By 2013, the first prototype of the GJ-11 Sharp Sword successfully completed its maiden flight, a milestone marking China's first public test of a heavy stealth combat drone. According to open-source accounts, the test took place at a southwestern facility and lasted around 20 minutes. Though brief, it demonstrated that China's domestic capabilities in aerodynamics and automated flight control had reached a mature operational level. From a classified blueprint, GJ-11 quickly evolved into a symbol of China's aerospace transformation. It is more than a UAV, it is a testament to indigenous high-tech development, once thought achievable only by nations with established defense industries. Strategically, GJ-11 signifies a turning point. China's formal entry into the select group of nations alongside America, France, and several European countries capable of designing and fielding stealth UCAVs. In the modern defense ecosystem, this achievement carries profound meaning. It represents control not only of airspace, but also of the information and electronic warfare domains, where human pilots are increasingly giving way to intelligent machines that can see, decide, and react. From this point on, Sharp Sword ceased to be a standalone project. It became the foundation for a new generation of intelligent combat UAVs. It marks the beginning of a new era in China's military aviation, one where silent wings and smart algorithms are quietly redefining strategy, data, and technological power in the 21st century. GJ-11 employs a blended wing body architecture, a configuration where the fuselage and the wing merge into a single, continuous aerodynamic surface. Technically, this design simultaneously reduces radar cross-section and optimizes the lift-to-drag ratio, allowing the platform to achieve longer endurance with the same fuel load. Rounded leading edges, concealed joints, and surfaces coated with radar-absorbing materials are the primary low observability measures, while the blended geometry improves stability at cruise speeds and at high flight ceilings. In design logic, GJ-11 shares conceptual similarities with Western flying wing platforms, such as the Northrop Grumman X-47B and the RQ-170 Sentinel. All three favor eliminating conventional tail surfaces to lower radar returns and enhance aerodynamic efficiency. The difference lies in operational philosophy. The X-47B was a naval demonstration platform designed for carrier launch and recovery. The RQ-170 is oriented toward covert high-altitude reconnaissance, and GJ-11 is conceived as an integrated unmanned combat aerial vehicle. combining active surveillance and internal weapon carriage. In short, similar silhouettes hide distinct mission goals and supporting subsystems. At the technical core, GJ-11 relies on an automatic flight control system with a fly-by-wire architecture, redundant flight controllers, and nonlinear guidance algorithms to ensure stability across all flight regimes. Advanced composite materials play a dual role, reducing structural mass and absorbing radar energy. An internal weapons bay keeps the external surface smooth, avoiding the radar penalty of external stores. Avionics are arranged with distributed redundancy to reduce the risk of loss of control. Artificial intelligence and multispectral sensing form the bridge between aerodynamics and intelligent operations. Machine learning algorithms process data from electro-optical cameras, infrared sensors, miniaturized active electronically scanned array radars, and electronic sensors performing sensor fusion to build a real-time environmental picture, assess threats, and make guidance or autonomous mission decisions within predefined limits. At high altitudes, where air density falls, the flight controller and AI adjust angle of attack, airspeed, and bay configuration to preserve performance while minimizing detectability. The notion of silent design extends beyond physical form. It must include electronic countermeasure capabilities, software security, and distributed network architectures to sustain operations in contested electromagnetic environments. In modern electronic warfare, a stealthy unmanned combat aerial vehicle is not merely an aerodynamic problem, but a system-level challenge from materials and mechanics to software and data working together to maintain low observability and survivability in a digitized battlespace. Estimated figures about the GJ-11 usually appear as open-source approximations and should be read as capability indicators rather than official specifications. Based on public reports and analytical assessments, the platform's payload capacity is estimated at about 4,400 pounds. Distributed across 2 internal bays, an internal weapons bay configuration allows the carriage of guided bombs using satellite navigation from Beidou, small air-to-surface missiles, and electronic warfare packages such as decoys. Placing stores inside the fuselage preserves a smooth aerodynamic exterior and limits increases in radar cross-section during operations. On operational reach, open-source estimates place combat radius in the range of 930 to 1,240 miles, a service ceiling above 39,400 feet, and a cruising speed of roughly 620 miles per hour. With these sorts of performance parameters, GJ-11 is designed not only for long endurance, standalone missions, but also to perform layered tasks, from sustained reconnaissance to precision strike and selective electronic disruption. What makes the platform powerful in practice is its data network and automated decision system. GJ-11 does not operate as an isolated flying object. It is a node within a larger ecosystem linked to navigation and collection satellites, ground radars, lightweight reconnaissance drones, and analysis centers. Together, they execute a closed-loop intelligence, surveillance, reconnaissance to strike-to-assessment cycle. Sensors collect information. Algorithms analyze and prioritize targets. Actions follow weapon release or electronic attack, and post-strike data are gathered for effectiveness assessment. At the technical level, communications latency, data link bandwidth, and the availability of transmission channels determine how much autonomy the system can assume. When latency is low and bandwidth is ample, decision-making can be distributed, part processed on board the platform and part at the control station or central processors. Conversely, in contested or degraded communications environments, GJ-11 relies on predictive algorithms, fallback operating modes, and pre-programmed behavior policies to maintain safety and accomplish tasks within permitted bounds. Multispectral sensor data, electro-optical, infrared, miniaturized active electronically scanned array radar, and electronic signals when fused through sensor fusion algorithms enable more accurate target identification, reduce false alarm rates, and support rapid decision-making. However, this capability also demands strong edge processing capacity and robust cyber protections because data are the decisive factor, and preserving the integrity and authenticity of data streams determines the platform's survivability and operational effectiveness in a digitized combat environment. In short, GJ-11's real strength lies at the intersection of internal payload carriage, extended operational reach, and most importantly, network data capability. That combination turns a stealthy flying wing into an active, decision-capable link within the ISR to strike to assessment chain. Open source imagery shows GJ-11 prototypes appearing with folding wings, a design detail commonly seen on carrier-capable aircraft where deck and hangar space are limited. Folding wings not only save room when stowed in a hangar, they are also a strong indicator that a naval variant of this platform is being considered for operation from modern carriers referenced in open materials, for example, Type 003 or test beds for future carrier classes. Adding a folding wing mechanism typically requires reinforced wing structures, reliable mechanical locking systems, and wing position control systems that are compatible with the harsh carrier deck environment, all aspects that public technical analyses describe as estimations rather than confirmed specifications. The link between a naval GJ-11 variant and an electromagnetic aircraft launch system (EMALS) becomes apparent when comparing the launch energy requirements for a stealthy blended wing configuration at full payload. An electromagnetic aircraft launch system, if fitted aboard a carrier, delivers a smoother, more controllable launch than traditional steam catapults, reducing structural shock on the airframe and enabling the launch of heavier unmanned platforms. For recovery, open source scenarios suggest options such as automated controlled recoveries or arrested recovery via tailhook and cable systems. However, the exact methods are typically withheld in internal documents, so public descriptions should be read as educated estimates of technical feasibility rather than operational procedures. Strategically, a navalized GJ-11 would enable stealthy, oversea watchful eyes, expanding reconnaissance coverage and projecting mission capability from a mobile platform thousands of miles from shore without risking embarked pilots, a capability that boosts operational mobility and reduces direct personnel exposure. In a networked operational model, a carrier could function as a command node that launches coordinates and recovers UCAVs in rapid ISR to strike to assessment cycles, improving tempo and flexibility for the fleet. By comparison, the MQ-25 Stingray of America was developed mainly as a carrier-based unmanned aerial refueling tanker to extend the range of crewed aircraft, a practical step focused on force extension rather than stealthy combat performance. European programs such as Neuron and Tyrannus represent research and pre-production demonstrators oriented towards stealth UCAV concepts and autonomy. They pursue similar technology goals but differ substantially in scale and carrier integration ambitions. Overall, if a naval GJ-11 comes to fruition, it would combine stealth, internal weapon carriage, and deck launch capability, marking a major step toward integrating UKVs into modern carrier battle groups. All of the above is drawn from open source reporting and public analyses. Numbers, performance claims, and functional descriptions should be treated as estimates for the purpose of technical assessment rather than as confirmed official data. Open source observations indicate that the Shagatsi Base in Tibet sits at an altitude of roughly 12,400 feet above sea level, with a runway length recorded at about 16,400 feet, figures that place it among the longest and highest runways in the Asia region. Those geographic features make Shagatsi a distinctive test site, not only a training field for regular squadrons, but also a natural, operational laboratory for validating the performance of stealth platforms, especially when they operate in thin air and under harsh environmental conditions. High-altitude terrain presents a broad set of technical challenges. Reduced air density lowers lift for some wing configurations, forcing flight control systems to adjust angle of attack and flight paths to maintain stability, which means flight control algorithms and the fly-by-wire system must be tuned for low-density conditions. Jet engines operating at lower ambient pressure face shifts in performance. Air intake and combustion efficiency drop relatively, increasing demands on inlet design and thermal management. Large temperature swings between day and night also affect electro-optical and infrared sensors, sensitivity, background noise levels, and system warm-up times are all impacted, requiring more complex calibration and stronger signal processing algorithms. Additionally, the plateau environment can challenge communication systems. Transmission links are influenced by atmospheric conditions and pressure differentials, highlighting the importance of backup channels, advanced data compression schemes, and robust edge computing to sustain operations when central links degrade. Materials and structures must also tolerate wide thermal cycling, which affects the longevity of composite joints and mechanical assemblies, such as folding wing latches or weapon bay doors. Open reporting notes that GJ-11 appearances at Shigatse frequently occur alongside the WZ-7 Soaring Dragon reconnaissance platform, providing evidence of joint testing for manned and unmanned coordination and data network interaction under real high-altitude conditions. This pairing enables evaluation of the full intelligence, surveillance, and reconnaissance to strike-to-assessment cycle in an environment with a high risk of link loss and fast-changing sensor conditions. Shigatse's role therefore goes beyond that of a routine test base. It is where engineering solutions are validated to ensure a stealth platform can sustain performance when confronted with severe physical variables from flight control, propulsion dynamics, and sensors to data links. Every trial there is an integration test of aerodynamics, materials, and artificial intelligence, helping refine a platform so it performs reliably in the most realistic operating conditions rather than only in laboratory settings. The concept of intelligentized warfare condenses the shift from merely collecting and transmitting information to turning data into automatic, real-time decisions. At its core is the fusion of four elements: artificial intelligence to analyze and forecast, big data as the foundational information source, a distributed sensor network from satellites and radar to airborne and ground sensors, and the capacity for instantaneous analysis and decision-making. When these components are tightly networked, military systems no longer simply respond step-by-step to orders. They begin to automate certain tactical decisions within pre-programmed bounds and under human oversight. From a technical perspective, GJ-11 fits this strategy because it is designed as a sensor-to-action node inside a larger ecosystem. The platform can operate in a manned-unmanned teaming model, that is, coordinated operations between crewed aircraft and unmanned aerial vehicles. In a manned-unmanned teaming network, a crewed fighter such as J-20 can act as the commanding integrator, ingesting data from multiple GJ-11 units and allocating tasks, for example, assigning strikes, electronic jamming, or imagery collection based on a continuously updated target picture. This capability relies on several key enablers: sensor fusion combining multispectral data, edge computing to reduce latency, and classification decision algorithms that permit mission tasking by priority levels. An illustrative scenario from open sources. In a coordinated mission, a J-20 flies as the command node to gather battlefield context. A forward screen of GJ-11 platforms conducts electronic warfare to blind enemy sensors. Then GJ-11 switches to precision employment using data from satellites and ground radar. Sensor data are shared in a feedback loop of ISR to strike to assessment, where post-action results are analyzed at the edge to adjust subsequent steps. Throughout the cycle, AI filters and prioritizes information, compressing the timeline from detection to action. This trend is reshaping global platform design. Software, network architecture, and data security now stand alongside aerodynamics and propulsion as primary design drivers. Platforms must meet interoperability standards, support safe algorithm updates, and tolerate electronic warfare effects. Priority shifts include modular sensors, redundancy, strong encryption, and the ability to operate under degraded communications. A crucial point is governance. Although systems may execute local decisions, humans must retain supervisory control and set operational limits to avoid unintended consequences. Ethical, legal, and safety considerations therefore become imperative in an era when unmanned systems do more than fly. They begin to think within boundaries established and overseen by people. In recent years, China's unmanned aerial vehicle development has not proceeded as isolated projects, but as a systematic, end-to-end industrial ecosystem. At the center sits the Aviation Industry Corporation of China, AVIC, which combines production plants and research centers such as Hongdu and Shenyang, working closely with electronics groups like CETC and a network of institutes focused on artificial intelligence, materials science, and defense electronics. This model enables a rapid handoff from laboratory research into synchronized design, production, testing, and deployment, airframe design, materials, radar, navigation systems, and software are developed in parallel rather than in separate contractor silos. The production strategy is organized as a clear value chain, starting with small reconnaissance UAVs that collect data and validate sensors, moving on to stealth UCAVs such as GJ-11 for precision strike roles, extending to naval UAVs with folding wings for deck operations, and ultimately expanding into swarm drone groups for distributed tasks and sensor saturation. Each product layer is designed not merely as a standalone platform, but to operate inside a common data network, reusing sensor technology, processing software, and internal communication standards. On the technology side, open source reporting indicates heavy investment in lightweight, radar-absorbent composite materials that both cut weight and optimize radar cross-section. There is parallel development of miniaturized active electronically scanned array radars to retain active sensing while reducing power demands, and integration of navigation, positioning, and communications networks built on the domestic Beidou satellite system, complemented by C4ASAR command, control, communications, computers, intelligence, surveillance, and reconnaissance frameworks to connect edge data with central nodes. Beyond hardware, large investments in defense-oriented AI software, combat simulation tools, and automated testing suites are critical enablers for faster commercialization and standardization. Compared with Western aerospace groups, the most striking difference is scale and vertical integration. European and American firms typically specialize in distinct domains: radar, automotive systems, aircraft, and collaborate across international supply chains. In contrast, China's model, guided by AVIC and state institutions, can marshal large domestic resources to integrate design, manufacturing, testing, and mass production under one national roof. This yields faster deployment cycles and competitive unit costs, but raises questions about international standardization and cross-border interoperability when exporting or cooperating internationally. In short, the industrial front behind GJ-11 is not just an assembly line. It is a coordinated technology, finance, and human capital network organized to turn stealth UAV concepts into operational, mass-producible systems. Every advance in materials, compact radar, or data networking is embedded in a long-term plan to make these platforms core components of a digitized combat architecture. The journey from a classified technical draft to a flying prototype seen in open-source imagery paints a vivid picture of transformation. GJ-11 is not merely the result of a single aviation program, it is the outcome of technological convergence, aerodynamics, materials science, electronics, artificial intelligence, and data infrastructure all fused into one. From the earliest design sketches to field tests and its appearances at high-altitude bases, this platform has gradually taken shape as a technical symbol, a flying wing that blends stealth with deep sensor and data integration. To view GJ-11 as just another aircraft misses its core essence. It is a system where software and data define performance more profoundly than shape or propulsion. At the operational level, GJ-11 represents a paradigm shift in modern military design, prioritizing networked, data interactive platforms capable of dispersed yet synchronized operation across the ISR strike assessment cycle. Its internal weapon base, aerodynamic stealth, and edge processing capabilities allow it to execute multiple missions under one configuration, from intelligence gathering and electronic warfare to precision strike operations. Yet what truly sets it apart lies in its software and data integration. AI-driven sensor fusion and adaptive communication protocols transform it from a manually piloted tool into a decision-making node within a larger digital command structure. This marks a broader transformation in China's defense industry, from imitation and localization to independent design and systemic integration. The focus has shifted from simply producing aircraft to building industrial ecosystems capable of turning ideas rapidly into operational assets. Investments in composite materials, compact phased array radars, and indigenous data navigation frameworks underscore this direction. In today's defense race, competition is no longer just about engines or aerodynamics. It's about software integration, speed, cybersecurity resilience, and algorithmic adaptability. Ultimately, GJ-11 symbolizes an era when military platforms are becoming increasingly intelligent aircraft that not only fly, but also process, analyze, and react in real time. This evolution introduces both technical and ethical challenges: securing data, ensuring software sustainability, and defining legal boundaries for autonomous decision-making. All interpretations here are drawn from open-source materials for technological analysis. Figures and specifications should be understood as estimates rather than confirmed data. As technology continues to converge, one question looms large. How will societies and the international community redefine safety, transparency, and control to ensure that automation serves stability rather than spreading risk in the age of digital warfare? From a design once cloaked in secrecy, GJ-11 has emerged as a symbol of the new age of automation in aerospace, where data, artificial intelligence, and physics converge to redefine humanity's role in the skies. Every aerodynamic curve, every algorithm in its system reflects the evolution of technology, no longer a story of speed or range, but one of intelligence, autonomy, and precision. As machines grow increasingly capable of understanding the battlefield, one question remains: are humans truly ready to trust the decisions made by artificial intelligence? Share them in the comments below. Don't forget to hit subscribe to stay updated on the latest insights into technology, national strategies, and innovations shaping the future. Top 10 Discoveries Official will be back with untold stories, projects that push boundaries, and quiet revolutions with global impact. See you in the next video.